Here we have a conservation of energy example involving multiple objects moving together. So we have two boxes, a 5 kilogram and 2 kilogram box, connected by a rope. As usually, we'll say the rope is massless and that it's passing here over a massless, frictionless pulley. And we will also assume the ramps themselves are frictionless. The 5 kilogram starts near the top of its ramp, and as it slides down, it will pull the 2 kilogram box up its ramp. We want to determine the speed of each mass once the 5 kilogram box reaches the bottom of its ramp. So we could treat this as a force problem, but it would be a little bit tedious. I mean, we have two inclines here. They are at different angles, so we would need to break force of gravity into components for each box. It gets a little bit tedious. So instead, let's look at how to treat this problem as a system problem, but from an energy perspective. And remember, what makes a system perspective useful, either for forces or for energy, is when the two objects will have the same acceleration. And that is certainly the case here. As the 5 kilogram moves, this rope does not stretch, so if the 5 kilogram moves 1 inch, the 2 kilogram also has to move 1 inch in that same amount of time. Both boxes will move together. So applying conservation of energy, first thing I want to do is define my initial and final moments. The initial moment is what's shown here, 5 kilogram at the top of the ramp, 2 kilogram at the bottom. The final moment will be after the 5 kilogram reaches the bottom of its ramp, and as it's doing that, the 2 kilogram will have been pulled 1.2 meters up its ramp. Define our system. It'll be the 5 kilogram box, the 2 kilogram box, the rope, and Earth. Include Earth because we have height changing, and I want to talk about gravitational potential energy. Include the rope so that it's clear that tension is an internal force. We don't need to worry about tension externally as something that might do work. Next, we want to identify any external forces. The normal force is an external force. So the ramp is exerting a normal force on the 2 kilogram box. This ramp is exerting a normal force on the 5 kilogram box. However, the normal force is perpendicular to the displacement. Normal force perpendicular to the surface of the ramp. The boxes are moving along the ramp. So anytime the force and displacement are perpendicular, you get a work of 0. So even though the normal force is an external force in this problem, it does not do any work. Over here, I'm going to take a minute and just write out the height of our boxes at each moment. So taking the bottom of the ramp to be a height of 0, 2 kilograms starts out at a height of 0. The 5 kilograms starts out with a height not of 1.2 meters, but we want the vertical height. So 1.2 sine 45 degrees. 5 kilogram box starts out with a height of 0.85 meters. At the final moment, 5 kilogram box will be at the bottom of its ramp at a height of 0. The 2 kilogram box will be up along its ramp at a height of 1.2 sine 30 degrees, giving us a final height of 0.6 meters. Turning to our conservation of energy equation, both boxes start out at rest, so initial kinetic energy is 0. Initial GPE, we have mgh for the 5 kilogram box. Initial GPE for the 2 kilogram box is 0. No elastic potential energy because there are no springs anywhere in our system. No work done on the boxes because there are no external forces that are not perpendicular, yes. The only external force is the normal force, which is perpendicular to displacement. So work is 0. Tension is an internal force because the rope is part of our system, and gravity is an internal force because the Earth is part of our system. Moving on to the final moment, we have 1/2 mv squared for the 5 kilogram box, 1/2 mv squared for the 2 kilogram box. That is our final kinetic energy. The boxes are connected by a rope that does not stretch, so they both have the same speed at the end of the problem. GPE for the 5 kilogram box is 0 at the end of the problem, but it is mgh for the 2 kilogram box. And again, elastic potential energy at the end of the problem is 0 because we have no springs anywhere in the problem. Solving this for speed, we get that both boxes will be moving with a speed of 2.92 meters per second once the 5 kilogram box reaches the bottom of its ramp.